Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about the thermodynamics of mixing together two different substances to make a solution. So when we're trying to evaluate how favorable it is to form a solution, we're going to be looking at three key properties. So the first of which is going to be enthalpy. And as with most things enthalpically related, this is going to be a measure of, do I have stronger IMFs in my product or my reactants? So am I producing a net set of stronger IMFs in between the solute and the solvent than the solute and the solvent have to themselves? The second component is going to be entropy. So is the solution more disordered than the starting materials? Most of the time, the answer will be yes, but not always. And then finally, if these two end up disagreeing about the favorability of forming a product, it comes down to temperature. Does enthalpy or entropy matter more? So we're going to be collecting a lot of what we talked about last chapter, and putting it together in a nice package. So let's go ahead and start by looking at enthalpy. So in order to produce a solution, one of the things we can do is split this up stepwise into all of the individual components. So the first thing I need to do is take my solute and I have to break all of the IMFs, which is going to be hard. Then I have to take my solvent and I have to break all of its IMFs into breaking it into an individual component. Both of these processes will always be endothermic. It will always take energy to break apart a system. However, one of the key things is that these two individual separated solutes and solvents will end up mixing together to make a solution. And this process will always be exothermic, because breaking bonds always takes energy, making bonds always releases. And so the big question when we're looking at a reaction is, did I make better bonds than I broke? And we can do this by adding all of these processes together. Positive, positive, negative. Am I more negative than my two positive steps were positive? So in order for a reaction to formation of a solution to be exothermic, so be energetically favorable, what I need is for the solution to be more favorable than the individual components. So a good way of thinking about this is that I have to make sure that the solvent and the solute like each other more than they like themselves. So would they rather hang out with each other than they would to be on their own? So in practice, this tends to lead to the principle that like dissolves like. Because if the intermolecular forces are fairly similar, then they're going to get along great. If they're very dissimilar, then we run into problems, because it turns out that, water doesn't really like grease. So we can think about things like what would happen if I mixed HCl with water. So HCl is very polar. It's a fairly unstable bond. And so if I put a very polar substance into something that makes a lot of good hydrogen bonds, we're in pretty good shape. And as a result, as you may remember in practice, if you put HCl in water, this reaction always tends to be fairly exothermic. So it produces a lot of energy, which means that you went downhill in energy, and this is going to be a favorable reaction. Now, what would happen if I put a nonpolar substance like grease into water? Well, at this point, it turns out that water likes itself plenty fine. Grease kind of likes itself, but water really doesn't like grease. So this last component is really missing. And as a result, you have to put in a little bit extra energy to make grease dissolve in water. And it's one of the reasons why, if you're trying to clean greasy pans, you should always use hot water to overcome that endothermic barrier. So when trying to figure out the actual enthalpy of these reactions, most of the time you can go ahead and determine these directly, and they can be found in a lot of literature sources. However, it can be a little bit tricky, as they're fairly dependent upon individual circumstances. So let's take, for example, if I have something like glucose. So glucose, which is a nice polar sugar molecule, if I put it in water, it takes a little bit of energy, so about 5 kilojoules of energy, which makes sense because glucose is fairly polar, so it likes water, but doesn't like water quite as much as it likes itself, because it has those fairly nonpolar things, and water gets along with it, but would rather hang out with itself. So this process is slightly endothermic. Now, one of the big notable exceptions for trying to just determine enthalpies of solution by looking them up in the literature is going to be when looking at the enthalpies of dissolution of ionic species. These can go ahead and be calculated by enthalpies of formation, because if I dissolve an ionic species like HCl in water, it immediately breaks apart into cations and anions. So again, for any sort of strong electrolyte. So in this case, if you've got the enthalpy of formation of each of your product individual ions, remembering the enthalpies of formation of ions are always given with respect to the enthalpy of formation of a proton being 0. And then you subtract out whatever the molecular species is, whether it comes from a solid or a gas. If you want more details and a good review of how to calculate the enthalpies of solution, go ahead and please watch my video from last semester. However, it turns out enthalpies don't determine everything. We also have to take into account entropies. So if I'm mixing together two substances, I need to also figure out, in addition to am I making or breaking, making good bonds and breaking bad ones, I also have to figure out, is the system becoming more or less disordered? And so this is largely going to depend upon the initial and final states of matter. So for example, let's say I'm mixing together two different gases. So if I'm mixing together two gases, I'm not really breaking any IMFs or making any IMFs. And what I end up with is a nice disordered mixture of the two species. So mixing together two gases will always have a positive entropy, as I essentially am letting both gases expand. However, let's say that I've got something like O2 and I want to try and dissolve it into water because I want my little fishies to be able to breathe. Well, this is going to have a negative entropy, as gases have very high entropies and aqueous species have moderate entropies. So this is an example of the formation of a solution leading to a decrease in entropy, and is probably the most common example of this metric. Because much more common is if I imagine mixing together two liquids, similar to mixing together two gases, what I'll end up producing is a system with slightly higher entropy, as my liquid ethanol can expand into an environment of water. And similarly, if I'm going to be dissolving any solid in a liquid, this will always be an entropically favored process, as it goes from a very confined state to a very free one. So this makes it fairly easy to find the signs for the entropies of the system. However, the exact values can be a little trickier to measure. This leads us to the real question of trying to figure out exactly how favorable it is to form a solution. So not too surprisingly, most favorability and spontaneity always comes down to Gibbs. But if we know my enthalpy, my entropy, and my temperature, I should be able to find the Gibbs of mixing two different substances to form a solution. So if I know the signs for my enthalpy and entropy, I should be able to have a good guess about how and when I should make the formation of a solution be favorable. However, I do want to make sure that you note that even if I have a positive or unfavorable Gibbs of solution, you may see some mixing occur. However, it will be what we'd call poorly soluble, as it won't be that favorable. So let's go ahead and start by looking at the mixing of one of the simplest sets of substances, mixing together two gases. So let's say I've got two gases, each in a separate container. I want to end up opening the block and letting them mix together. So how much would I expect A to join B or B to join A? In this case, I can go ahead and look at Gibbs. So let's take a look at enthalpy. So if I've got two ideal gases, I have no IMFs in my initial solution and I have no IMFs in my resulting solution. So enthalpy doesn't matter. And we're going to find any number of cases where you have similar IMFs in between reactants and products. And in this case, we can treat it like mixing of two gases. That means that everything's about the mixing, about the entropy of solution. And in this case, like we saw last chapter, if a gas is able to expand and occupy more volume, it will always be more favorable. So in general, if you're occupying more volume, have more options, we're going to see a positive entropy of solution. And since enthalpy doesn't play a role here, what we're going to find is that we'll have a net negative Gibbs, because remember that minus T, and the mixing of two gases will always be favorable. However, as a fun little notation, you increase the temperature, they'll mix even better. And so this is a reason why if you have, say, a balloon, you'd expect it to immediately expand as soon as you pop a hole in it. It's always driven by entropy. And this is a very common theme in mixing, is this entropically driven expansion. However, for the production of most of our solutions, we're going to find that enthalpy and entropy are going to really be at odds. And so this is going to play a big role in determining the favorability of forming a solution. So for example, if I'm trying to dissolve a gas into liquid like oxygen, well, in this case, I am making good IMFs, as I have no IMFs in the gas phase, and oxygen can coordinate to water. So this should be a negative value. However, entropy is also negative because I've lost space to move around in. So in this case, enthalpy says yes, entropy says no. If I'm trying to mix ethanol with water, in this case, the bonds, water doesn't like ethanol as much as it likes itself, as we saw, similar to glucose. So enthalpy says no, but entropy says yes, because the ethanol is expanding. It's moving into new spaces. And similarly, this happens for most ionic solids. You tend to be breaking fairly good ionic bonds and making weaker polar ones. So it's slightly positive. And similarly, the enthalpy will be slightly positive as you're expanding. However, it is worth noting there is a subset of ionic systems where these two signs can actually be reversed. So in these cases, you'll note that enthalpy says one thing, entropy says the opposite. And in these cases, temperature is going to play a key role. And so what we, by convention, what we tend to do is talk about the favorability of a reaction based on enthalpy. So a good way to look at this is if I have an endothermic reaction, such as putting a gas into water. In this case, if I have an endothermic reaction like salt into water, in this case, I have to put in energy. So if I go to higher temps, I have more energy to put in the reaction. And these systems will tend to be more soluble. More of that salt will dissolve at higher temperatures. Conversely, if I have an exothermic reaction, like mixing a gas into water, where I'm making better IMFs, these tend to be favored at low temperatures, where it makes a bigger difference to the surroundings if I'm producing energy. So again, exothermic reactions favored at low temps, endothermic reactions favored at high temps. However, one of the big things to keep in mind is that all of this just helps us get an idea of what the Gibbs is. The really useful part about Gibbs is it helps us figure out exactly how much of the product I end up forming. And next time, we're going to be focusing in on saturation, or exactly what concentrations of a solute I can drive into solution. Until then, take care.